Okay, so let's speak a little bit about countable set and infinite set and so on. So a set is countable if you can count the elements of the set, right? So think about just writing 1, 2, 3, labeling the element of the set by number 1, 2, 3, and so on. And if you can do that and reach all the elements of the set, then the set is countable. Formally, a set is countable if there is an injection between the set and the natural numbers. Okay, and of course, all finite sets are countable because you can just take them and order them in arbitrary order. If you want, just put them in dictionary ordering, and just say, first strings, lexicographical ordering, and just number them from, first, second, and last in this ordering, right? So good. So all those sets are countable. But then you can start asking much more subtle questions. For example, is it true that the integer grid is countable? Here we are looking on all the set that is the Cartesian product of the natural number by themselves, right? So a member of the set is a pair of two numbers, ij, which are both integers. And the easy answer is yes, by using the formal definition, right? You just define this function fij, which maps the pair ij to the number 2 to the i, 3 to the j, and it's very easy to verify that this mapping is 1 to 1. So indeed it's an injection, and it's not a bijection in this case, but we don't need a bijection, we just need an injection for countable sets. And as such, this set is countable. A much more satisfying proof follows from, visually. So think about drawing this grid. So it's an infinite grid. So I do only part of it because I don't have enough time to draw all of it right now, maybe later. And now all I'm going to do, I'm going to just draw a curve that visits all the vertices of the grid, right? The point ij is just a point in this grid, or the pair ij is a point in the grid. So I start at the origin, and then you start zigzagging, right? Right. You go to all the point in the I diagonal, then you move on to the point in the next diagonal, and you just keep zigzagging until you visit all the points. You have to be a little bit better in drawing than me to really visit all the points, but that's a technicality. So clearly this mapping sooner or later visits all the points in the grid, right? Or this is of course imprecise. More precisely, if you pick any point in the grid and you wait long enough, this zigzag path would come and visit the point. Okay. So this set is countable. And here we would in fact be interested in infinite countable sets. So those are called countably infinite sets to distinguish them from the finite countable sets. And in this case, a set is countably infinite if there is a bijection between the set and the natural numbers. Okay. And again, it's more convenient to think about countably infinite as you can enumerate the items of the set, right? By that I mean you can write down a program that would start outputting the strings. And if you wait for every element in the set, if you wait long enough, it would output the element, right? And you can just think about it as enumerating the set, right? Because the numbering of a string or element in the set is just going to be its number in the output, right? We are not allowing the output to repeat outputting the same string again and again, right? It has to output a string only once, and as such, it's such an algorithm enumerate a set, and if you can enumerate a set, then it's infinite and it's infinitely countable. Okay, so if we have an alphabet sigma, then sigma star is countable. And the idea of the proof is very simple, right? We can take sigma and think about sigma star, right? Now, the first naive thing is to say, well, this is just a collection of strings, it's a set of strings. We can just write down the strings in dictionary order, lexicographical ordering, but that doesn't quite work because you would never reach strings that have the second letter in the alphabet, right? Your dictionary would go on forever only with letters start with the first letter, so that's not good. But you can just use the definition of sigma star. So what is sigma star? It's the union of sigma 0, sigma 1, sigma 2, and so on, right? Sigma n if you want, and so on. And now what you do, you're going to enumerate all the string in the first set first, then you enumerate all the string in the second set, and so on. Since each one of those sigma to the I sets are finite, there's no problem enumerating them, so you enumerate them one after the other, and you continue enumerating them, right, going from bigger and bigger n, right? So clearly, this would enumerate all the string in sigma star. Again, by that I mean that for any string, sooner or later, this enumeration would encounter it. An algorithm outputting the strings in this order would output the strings. So this indeed shows that sigma star is countable. Okay, and here are some examples how it look like, right? So for 0, 1, you start with the empty string, then 0, then 1, then 0, 0, 0, 0, 1, blah, 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 and so on. Okay, and here is how it's with ABC. Okay, so here's an exercise. Is the set sigma star times sigma star countable? Well, or more precise, infinite countable. So think about it. Maybe stop the video and think about it before you continue to hear my answer, because I want you to think about it a bit. Okay, so the answer is yes. And the reason why it's yes, so one can prove it formally, but I'm not going to do that because this is painful, or, a bit painful. There is a much more elegant intuitive argument. So I'm going to assume that sigma, my alphabet, doesn't contain the following special letter: open parenthesis, closed parenthesis, and comma. Oops, I'm not very good in writing commas, unfortunately. That's it. Okay, so sigma does not contain these letters, and I'm going to define a new alphabet, which would be gamma, which would be the union of sigma and those three special characters, right? Now, gamma star, it's all the string over this new alphabet. This is, of course, countable, right? Because it's infinite countable because we just showed that it's infinite countable. Okay, so this is infinite countable, and it contained, of course, the set of strings sigma star times sigma star. Okay, now contain here means I mean it in double quotes because mathematically speaking this is not correct, but intuitively it's correct, and I would explain what I mean by that. So take a string x from the first term and take a string y from the second term, and this gives you a pair xy, right? Now I can interpret xy as a string, right? Open parenthesis, whatever the content of x is, comma, the content of y, and then close parentheses, right? So this I can write explicitly as a string, and this string is definitely a member. This definitely belongs into gamma star, right? So this shows that sigma stars times sigma star is indeed contained in gamma star, which means that it's and since gamma star is infinitely countable, it means that sigma star times sigma star is infinitely countable, right? Now what I really showed here, if you think about it, I showed an injection from sigma stars times sigma star into gamma star, and there is injection from gamma star into the natural numbers because it's infinitely countable. So putting those two mapping together, I get an injection from sigma stars times sigma stars into the integer numbers. And if you have an injection of an infinite set into the natural number, one can show that in fact there exists a bijection. Again, this is non-trivial, but it's known. And as such, there is a bijection between sigma star times sigma stars to the natural number, and the set is infinitely countable. So of course, this is a very painful way of doing it, but formally this argument works. But of course, this argument that I just gave about writing the string is it's the same argument essentially, but it's intuitively, hopefully, much clearer what's going on. Okay, now one can ask the same question about sigma star times sigma star times sigma star. Just think about that. I'm not going to answer that. That's kind of easy now. And here's a long list of other questions that you should be able to answer. Again, you should be able to answer it because you saw this stuff before. And so you should go through this question and verify that you know how to answer them correctly. Some of them are not immediate. You would need probably to spend some time refreshing your knowledge of this stuff. And that's it for now.